Prove that the number of primes is infinite. How many people tried this at home? Good, good, good. And now you know how to prove it? Okay. Can you name an early mathematician that proved this a long time ago? But I gave you the answer. I gave you the answer on MS Teams because you missed last class and I taught.
I've seen this.
Oh, you've seen this. Okay, yeah. So Euclid's proof. What's the name of Euclid's most famous series of books? The Elements. All right. So proposition 20 of book 9, The Elements. All right. Tejas, you ready? This was a question on the spring 2006 midterm, Math 135. You have a few minutes to prove that the number of primes is infinite. You don't have a lot of time. You've got to do this quickly. Okay, assume there's a finite set of primes. Ordered from smallest to largest, it's going to be P1, P2, up to Pn. So there's some finite set of primes. Let P be the product of all these primes, okay? Let Q equal P plus 1. All right? Now, case 1, if Q is prime, then F doesn't contain all the primes because it doesn't contain Q. There's a new prime that wasn't in the original set. Of course, Q is not in the original set because Pn is the largest prime in this finite set of primes, and Q is bigger than it, right? Q is larger than it, and it wasn't in that set. So that set was incomplete. It doesn't have all the primes. What about in case 2 when Q is not prime? If Q is not prime, then it contains some factor R, which is not Q and not 1. It's not a prime number, it's a composite number. So it has some factors, it has some prime factors in addition to Q and 1, or it has some factors in addition to Q and 1. And if it's a factor, then R divides Q. If R is a factor of Q, then R divides Q. So R has to be between 1 and Q because it's not 1 and it's not Q. So it's some prime number between 1 and Q. Okay, so if R divides Q, what is Q equal to? Q is equal to P plus 1. So R divides P plus 1. R divides Q, that means R divides P plus 1 because Q equals P plus 1. Okay, so R is less than Q. We determined that there because it can't be Q. It has to be less than Q. And if it's less than Q, if it's an integer less than Q, then it's less than or equal to Q minus 1. Q minus 1 is the last integer before Q, right? So it's less than or equal to Q minus 1. And Q minus 1 equals P, right? Q minus 1 equals P. We get that right from here. So R is less than or equal to P, right? All right. So if R is in the set F, then R divides P. Why is that? Because if R is one of these primes from the initial set, then R has, because P is the product of all these primes, if R is in that set, then R divides P because it's one of the factors in there, okay? So now R divides P, and R also divides P plus 1 because we proved that right here. R divides Q, and Q equals P plus 1, so R divides P plus 1. So now we use DIC. R divides PX plus P plus 1Y, all right? So R divides P, and R divides P plus 1, so it divides this integer combination. Now R divides P plus 1, so R divides P plus 1 minus P, because I said Y equals 1, X equals -1, so I have P plus 1 minus P, that's equal to what? Louder? 1. So R divides 1. What's the only number that divides 1? 1. 1 is the only thing that can divide 1. So we already said that R is a prime that is not 1 or Q. I mean, 1 is not a prime. So if I say R is a prime factor, I'm saying it's not 1, it's not Q. So how can you have a prime number that divides 1? It's impossible. 1 is the only thing that divides 1. So I have now basically the assumption that R is in this set P is false, because if R is in that set P, then R divides this capital P. Sorry, if R is in this set F, then R divides capital P. And if R divides capital P, then R divides 1, and it's not 1. Oh, what did I just do? Okay. If R divides capital P, and R is not equal to 1, then that means that R is a number that's not 1 and divides 1, which doesn't make sense. So that means that, so for any set of F primes, whatever that set is, I haven't told you which primes these are. That's just a finite set of primes. There's at least one prime missing. In case 1, it's Q that's missing. In case 2, it's R that's missing. R is a prime that's not 1 and not Q. And it's definitely not in this set, because if it's in that set, that implies that R divides 1, which is not true. All right, small note at the end. This is the idea behind Euclid's proof, but unfortunately, set notation wasn't invented yet. His proof was much less elegant, probably took way more pages. This is much more elegant proof. He didn't have any way to mathematically denote an arbitrary set of finite prime numbers, a finite set of prime numbers. So he wasn't able to do this, which we're able to do in just one line. He started with just 3 primes in his set, and then he kept adding more primes. And so this isn't exactly Euclid's proof, but it's the idea behind Euclid's proof. Put in modern notation, it fits onto one slide. All right, so that finite set of primes, no matter how many primes you have in that set, it's not enough. There's always at least one more. And then that's a new bigger finite set, but there's still primes missing from that one, either Q's or R's. There's something missing. And then that's a bigger finite set. There's still primes missing from that one. So there's an infinite number of primes. All right, you think you can do this in 10 minutes on the midterm? Okay, well, actually, this proof is in the course notes in chapter 6. So I think in that year when they did the midterm, that chapter might have been covered already. So it was just a proof from the course notes. That's why you've got to do every proof you can possibly find, all the extra problems, all the previous midterms, all the course notes exercises. If you do them all, then you've seen everything. A question can just show up on the midterm and then you already know how to do it. You just do it in 2 or 3 minutes, it's done.